Hello, my name is Anisa Syahirah Binti Azmi, and my matrix number is 2025304731, and I am from class 2301A.
Assalamualaikum. My name is Iman Sofea. My number metric is 2025-1304557 from group class CS 2301A.
We are Group 7, and today we will be presenting our final project for CSC 429 titled System Interrupt in Intel Core i7 Processor using EPIC. In this video, we will explain how system interrupts are handled in a multi-core Intel CPU, focusing on the Intel Core i7 12700K model. We will also describe how the EPIC architecture and how it improves system performance. A system interrupt is a signal that temporarily pauses the CPU current task so that it can respond to an urgent event like a keyboard press or USB input. Interrupts are critical for real-time responsiveness in checking or polling for changes. Modern CPUs like the Intel Core i7 have multiple cores, so to manage interrupts efficiently, Intel uses the Advanced Programmable Interrupt Controller, which we call EPIC. The EPIC system plays a vital role in distributing interrupts to specific CPU cores based on priority and availability. The EPIC systems replaces the older method using the 8259A PIC and PCI interrupt lines, which were slower, more limited, and often involve sharing the same interrupt line between multiple devices. EPIC allows each interrupt to be routed directly to the correct CPU core without conflicts, which increases system speed and also stability. This evolution from PIC to EPIC reflects how processors have grown more complex and more powerful. With many cores now operating in parallel, having a smarter way to direct and manage interrupts is no longer optional. It is a necessity. The Intel Core i7 12700K is a 12th generation desktop processor built on the Elder Lake architecture. It features 12 cores, 8 performance cores, and 4 efficiency cores, and supports 20 threads through hyper-threading. This allows the processor to perform multiple tasks at once while maintaining high speed and also efficiency. This hybrid architecture allows the processor to manage both heavy and light workloads by assigning them to the appropriate type of core. For example, background tasks like antivirus scans may go to efficiency cores, while demanding applications like video rendering are handled by performance cores. Because of this complex structure, managing interrupts properly becomes more challenging. That's why Intel embeds EPIC support inside each core, enabling fine-grained control over how interrupts are handled and which core responds to which signals. The EPIC system includes two main parts, the I/O EPIC and the local EPIC. The I/O EPIC is responsible for receiving interrupt signals from external devices such as keyboards, mice, USB devices, network cards, and so on. It can handle many more interrupt lines than the older PIC and also allows for better routing and control. The local EPIC resides inside each CPU core. Its role is to receive interrupt messages directed to its core, prioritize them, and notify the core to act. It also sends and receives inter-processor interrupts, IPI, for communication between cores. This dual structure, with I/O EPIC handling external interrupts and LEPIC managing core-specific actions, allow the system to distribute interrupt processing across multiple CPU cores efficiently, ensuring that the processor never gets overloaded or delayed. Each LAPIC operates independently but in coordination with others, which is essential for high-speed multi-core systems like the Core i7-12700K model. Now, we will explain how the epic diagram works step by step. We will also give simple examples to make it easier for you to understand. Let's begin with step 1. External interrupt, or we call IRQ or interrupt request. This is a physical electrical signal that notifies the system that attention is needed. For example, you press the letter A on the keyboard. At that moment, the keyboard sends an IRQ to the system to get the CPU's attention. It's like ringing the doorbell to get someone to open the door. Now, let's move on to step 2. The I/O epic receives the IRQ and chooses which CPU core should handle it. It does this based on a priority system and the availability of cores. For example, think of the I/O epic as a receptionist at office. When someone calls, the receptionist decides which employee is available and best suited to answer the call. In this case, the receptionist is I/O epic, assigns the call to core 1. Moving on to step 3. The I/O epic creates an interrupt message, which is a small packet of digital information. This message contains details such as the interrupt vector, which tells what kind of interrupt it is and which core should handle it. The message is then sent to the local epic inside core 1. For example, it's like sending an email or a text message saying, "Please handle this keyboard input." The message travels across the system bus to reach the intended core.
I will continue for the next step. Sometimes one CPU core needs to communicate with another core. This is done using interprocessor interrupt or IPI. This is especially useful in multi-thread tasks or when one core is idle and another needs help. For example, core 2 finishing its task and sending an API core 4. It like coworker ping each other on a messaging app when they need assistance. Now for the step 5, the local API inside core 1 receives the interrupt message and alerts the CPU. It puts the message into its interrupt request register IRR, checks its priority and signals the processor. Examples: think of the local API as a smart assistant who receives an urgent notification and immediately interrupt the boss CPU cores to handle it. And finally, step 6. The CPU core temporarily stop its current task and run the interrupt service routine ISR, which is a small program that handles the interrupt. After the ISR is complete, the CPU returns to the task it was doing before. Examples: Core 1 read the A key input, process it so that the letters show up on screen, and then goes back to the running your game or video. You can think of this whole flow like a manager assigning tasks to the right workers in an office. The I/O API is like the receptionist and Lapix, like a personal assistant, and each core is a worker. Once the job is done, everyone goes back to the what they were doing. This is to keep everything organized and efficient. Before we continue, we like to explain two parts of the diagram, the bridge and the PCI bytes, which are also important in the system architecture. The bridge, often called the chipset or system hubs, acts as central controller that manage the flow of data between the CPU and other parts of the system, including memory, graphic, and peripheral device. It links the system bus where the CPU and EPIC communicate to other technologies like PCI, or Peripheral Component Interconnect is a legacy standard for connecting external devices to the system, such as sound cards, network cards, and other hardware. Even though EPIC handles interrupt routing more efficiently now, the diagram includes PCI to show where the signals used to originate from and how they stay interface through the bridge. In summary, the bridge allows all these different components, including the I/O EPIC and PCI device, to communicate with the CPU smoothly. Without it, data from all the buses would reach the processor efficiently. The old system using PIC had shared interrupt lines and limited routing ability and no support for multiple CPU cores. This often led to conflict or slowdowns when multiple devices try to interrupt the CPU at the same time. With EPIC, each interrupt can be routed directly to the appropriate core, and multiple cores can process different interrupts at the same time. This parallel handling is a game changer for the system responsiveness, and EPIC also supports more interrupt vector, giving the operating system greater flexibility and precision with programmable priority level urgent tasks and handled immediately while less critical ones with. This kind of intelligent interrupt management is vital for multitasking, real-time performance, virtualization, and even low latency gaming. Imagine you are gaming while live streaming and downloading files at the same time. Each activity creates different interrupt signal from the mouse, keyboard, camera, network, and more. With Epic, each of these interrupt is directed to the best available CPU cores. Core 1 might handle the game, and Core 2 the camera, while the Core 3 the download, and so on. The system never get overwhelmed. So, in summary, EPIC allows modern Intel CPUs like i7 12700K to handle interrupt in faster, smarter, and more scalable way. It replaces old systems like PIC and enhances performance by routing interrupt directly to the best suited CPU cores. It supports multitasking, real-time communication between cores, and efficient use or of processing power. By embedding EPIC within each core, Intel ensures that its processors are prepared for the demands of modern computing, from gaming and content creation to enterprise level workloads and beyond. Thank you for listening to our presentation. We hope you now understand how system interrupts are handled in Intel Core i7 using EPIC. Assalamualaikum and goodbye.